Hi, Science 30s. So this is Unity Energy Lesson 3. And so at the top of your page in your notes, it should say nuclear energy. So starting off with this, it says describing the nucleus. So again, you would have seen all of the stuff in Science 10. You would have talked about the nucleus of an atom. The nucleus is the majority of the mass of an atom. So every atom has a nucleus composed of protons and neutrons. So usually I'll write it as P with a little plus because it has a positive charge, and N with a 0 with a slash through because neutrons are neutral, they have no charge. Um, the number of protons is actually the same as the atomic number. So in your periodic table, if you're peeking around, you'll see that every element has a different number. So carbon has a number 6 up in the top left-hand corner. That's its atomic number. Carbon has 6 protons. If something has 7 protons, it can't be carbon. It has to be nitrogen. So the number of protons is specific to each element, which is the atomic number. If you add the number of protons and neutrons together, that gets us our mass number. So the example that they have here is beryllium, so atomic number 4. Is beryllium, that 9 up at the top. If you look underneath the word beryllium, it says 9.01. Again, the reason that that's a decimal is it is an average of all isotopes of beryllium that are found. So that 9.01 means probably most of beryllium that's found is beryllium 9, but there's a little bit of, I don't know if it's beryllium 10 or beryllium 11, so that's why the overall average is slightly more than 9. So we would just say that its mass number is 9. So you kind of round it to the nearest number. So something like phosphorus, that's 30.97. You would round its mass number to 31. Because again, it's made up of your mass number is your number of protons and neutrons. You can't have, so for beryllium, we know beryllium has 4 protons. Your protons plus your neutrons is your mass number. So that's 9. So we know that needs to be 5 neutrons. And the reason, so that equals 9. We don't want to have 9.01 as our mass number right now because that would mean that you need 5.01 neutrons. You can't have 0.01 of a neutron. So again, the reason that that number is a decimal is it's an average of all isotopes. And again, an isotope of something has a different number of neutrons. We would have talked about that at the beginning during our review, but also in Science 10 and if you took Science 20 as well. So nuclear reactions change the number of protons. So we can use the P plus for protons. Another symbol, I didn't leave myself enough room, is we could write it as, so kind of like this, a 1 superscripted in front and a 1 subscripted in front as well. So 1 proton, and nuclear reactions can also change the number of neutrons. So again, I sometimes write it as N0, but the other way that we could write it is 1 N0, because again, when we have it written in this form, the number at the bottom is your number of protons. So in 1 proton, there's 1 proton. In 1 neutron, there's 0 protons, but it has a mass number equal to 1. A neutron has a mass number equal to 1 because 1 neutron provides 1 mass. 1 proton provides 1 mass as well. So it can change your number of neutrons, protons, and it can also emit energy in the process. So 3 types of nuclear reactions exist. So we'll talk about just radioactive decay today. So the 3 different types of decay. That's the first one. So radioactive decay. And we'll also talk about fission and fusion reactions next week. So radioactive decay, that's what we'll talk about today. So protons we know are positively charged. So if you have more than one proton, those should repel each other, right? Having lots of positive charges, those should have repulsive forces between them. However, there is a force called the strong nuclear force. That holds them together. The strong nuclear force acts over very small distances, short distances. So the nucleus, as the nucleus becomes larger, the protons get further from each other and have a harder time staying in the nucleus. So this is talking about big things that have lots of protons. So as the nucleus becomes larger, the protons get further from each other and have a harder time staying in the nucleus. So we're not talking about little things like lithium and beryllium. We're talking about big things like uranium and some of the other things that we'll look at. Lead is another one that we'll look at in a bit. So radioactive decay. Oops. Decay is the transformation of these unstable nuclei, so sometimes called radioisotopes, into more stable nuclei. This releases energy as radiation. If the radioactive decay creates a new element, then it's called transmutation. Which sounds like some sort of video game or Harry Potter thing that you can do, transforming one thing into another. So the example that we have there is the transmutation of uranium-238 to lead-206. And so this is used for giving a number to dating rocks, so saying how old a rock actually is. I forgot an O there. So used in geology in order to radio date rocks, figure out how old they actually are. So the transmutation of uranium-238 to lead-206. So we have the reaction written there. So again, just looking at those components. So atomic number 92 is uranium. Atomic number 82 is lead. Again, it's telling us uranium-238, so that's your mass number. So 238 is a mass number, and 206 is the mass number for lead. So this chart kind of breaks down the calculations that we've already been talking about. So again, protons is calculated by the atomic number. So the atomic number of uranium is 92, lead, atomic number 82. So that's how many protons are within it. So again, this is also giving us kind of our reaction, so reactants, products. So what we need to do is figure out how many protons have been lost or converted to energy. So 10 protons are lost within that reaction, right? 92 subtract 82 is 10. Neutrons. So the way that we calculate the number of neutrons again is your mass number subtract the number of protons or subtract your atomic number. So in your uranium-238, there are 146 neutrons. In lead-206, there are 124 neutrons. So to figure across that reaction, if we take the number of neutrons within the reactants and subtract the number of neutrons within the products, we have 22 neutrons to account for. So the lost protons and neutrons release energy in one of three ways. So the first one we're going to talk about, sorry, I'm going to pull this up. Sorry, I was going to pull something up, but we're just going to keep going with this sheet. So, oh, no, it's going to take forever. So what we need to do is account for those lost protons and neutrons and the energy that's released in one of three ways. So the first one that we're going to talk about is alpha decay. So alpha kind of looks like a fancy A, looks like a fish, kind of, I don't know. So that releases alpha particles from the nucleus. So we'll talk about what an alpha particle kind of looks like. So an alpha particle is made of two protons and two neutrons. So what that actually looks like, if you're peeking around in your periodic table, if you look at helium, so helium in group 18 there, atomic number 2, so we know that 2 means 2 protons, 4 means that its atomic mass is 4, so that actually would also need to have 2 protons. So an alpha particle looks like a helium nucleus. So in an example here, we have uranium. So finding uranium in your chart, so it's atomic number 92. It's way down actually in the actinide series, so in that part of the periodic table that's below. So atomic number 92, and it is actually decaying, we'll call it decaying, into thorium. So atomic number 90, it's just 2 spaces over, and a helium nucleus. So this is our alpha particle. So that's our alpha particle. And so what we see, let's kind of analyze. So our mass number of our reactant, again, that mass number is the top part, is 238. Our atomic number of our reactant, I might have said the word product there, I meant to say reactant. Our atomic number of our reactant is 92. So now we can look at our products. So our products, our mass number is 234 for thorium and 4 for helium. And our atomic number for our products is 90 and 2. So what we see is the atomic number overall remains the same, and our mass number overall remains the same. But what we have is we have different products. So what's actually happening if we look at our thing that's being produced, so what's the production of our transmutation? We have the production of a helium and whatever our other product is. So just to kind of analyze, our mass number of our product will be 4 less. Oops, 4 less. And our atomic number will be 2 less. And then what we see, so what I'm saying is our mass number is 4 less, our atomic number is 2 less, and then our other product will be a helium. So to account for that 4 less in the mass and 2 less in the atomic number. So that's alpha decay, and alpha decay is most common or more common in heavier nuclei. So this is common in heavier nuclei. So something like uranium, you see mass number of 238 is pretty high. So this happens quite often in heavy nucleus or nuclei, again, because of this, as we had up here, this strong nuclear force. So as there's more and more protons in something, so this, again, uranium has 92 protons. As they get farther apart, that strong nuclear force is less likely to be holding it together. So the next type of decay that we can have is beta decay. So beta is like a super fancy bee, releases alpha particles, beta particles from the nucleus. Beta occurs when a neutron, oops, that deleted our neutron symbol. So beta decay occurs when a neutron, so again, the way I represented a neutron. So neutron has one mass number, no protons, no atomic number, so that's our neutron. It's converted into a proton. Hopefully that still showed up in your notes. So the way we represented a proton has a mass number of 1 and an atomic number of 1. So that's a proton and an electron. I'll just point to the electron down here. So the electron is actually what we will call, or the electron is our beta particle. So beta decay, again, this is an example of beta decay. So we have carbon-14. Carbon-14 is actually really important in radiometric dating of organic remains. And so we won't talk about that. Again, that was Science 20, but we have carbon producing nitrogen and a beta particle. So that will represent as an electron. So again, looking at our mass number and our atomic number of our reactants and our products. So our mass number of carbon is 14. Our mass number of our products is 14 plus 0. Again, an electron has essentially no mass. Our atomic number of carbon is 6. Our atomic number of nitrogen is 7, but it's more complex than just the atomic number, actually, being a proton, but what we have is a -1 represented by our electron. Our atomic number is actually related to the charge of the nucleus. So in this case, since we have an extra negative with the electron, 7 minus 1, which is 6. So we see that overall our mass number does not change. Our atomic number does not change with the production of that electron. So if we're trying to figure out what our other product is, so sometimes you'll be given your full reaction, sometimes you'll have to figure out what the actual other product is, or even what the reactant is. So overall, this will have an unchanged mass number. But the atomic number will increase by 1. So this went from an atomic number of 6 to an atomic number of 7. Whenever we have an atomic number of 7, that represents a neutron. So an unchanged mass number, but atomic number increases by 1. So that's beta decay. So again, beta particle is an electron. Alpha particle is like a helium nucleus. The last one is gamma radiation. So gamma radiation is energy as EMR. So again, we missed the physics unit. We talk a lot about EMR in the physics unit usually. So this is called electromagnetic radiation. So this isn't releasing a particle. It's not releasing matter. It's releasing radiation. So it's releasing energy. So this is not matter. It's different than alpha and beta decay because in alpha and beta decay, we had matter being released. An electron, a helium nucleus, that's matter. This is actually energy being released. So this gamma radiation sometimes will come from beta decay, but most of the time from alpha decay as well. So producing gamma rays does not change the number of protons or neutrons, but it is caused by the change in the number of protons and neutrons. So gamma ray itself does not change it, but it's caused by the change in it. So what we will actually see in these is the release of just gamma rays. So gamma looks like a fancy Y. And again, that's just releasing energy as radiation, which we'll talk a lot more about in the next 2 days. So the reason that gamma rays are released is basically just moving from a really unstable state to a more stable state. And so looking at this one, so we have what we see here, this is beta decay, right? So the loss of a beta particle or the release of a beta particle as an electron, but it also is accompanied with gamma radiation. So these will go hand in hand, having beta or alpha decay with it, but it'll just have the production of energy as well. So we see that our reactant has a mass number of 24. Still the same in the product for our beta decay because an electron has no mass. Atomic number is 11. Oops. So 12 plus a negative 1 is still 11. So it's the same situation as we kind of had with the beta decay, but this gamma ray is the big part of it. So releasing a whole bunch of energy. And we know that energy can have some problems. The release of gamma radiation can actually be, it's ionizing radiation, so can create pretty big issues depending on what it interacts with. So there's a little summary chart on the next page. I'll just kind of zoom through it. And then there are questions. So there's question 1, 2, 3, 4, 5, and then it says do the questions on page 506 to 509. You can kind of skip over that, but I would definitely do questions 1 through 5 just in your notes just to figure out the reaction. And I also sent you an assignment sheet as well. I forget, I think it's called radioactivity, and it's just one side. So once you've done the once you've done the questions in this notes package, make sure you do that worksheet and send it back to me. So just a little bit of a summary. So alpha decay is an alpha particle, which we said looks a lot like a helium. Beta decay are beta particles. And this one is releasing energy. It will be with one of these two. So a beta particle we represented like an electron, so has an overall negative charge. The amount of energy associated with decay. So this is low energy, medium, and this one is very high. Yes, I am yelling. It is very high. So the distance that this energy can travel, so this is a super short distance. So it's alpha decay is stopped by like skin paper. Can't do a whole heck of a lot. Distance for beta decay, medium, stopped by wood walls. Gamma radiation can travel greater distances, and so it needs to be stopped by concrete, lead, something like that to stop that radiation that is released. How do you know that each of these occurred? This is what I was kind of writing. I'm not going to have enough room. So atomic mass decreases by 4. So, and again, that's because number of protons and neutrons in daughter material is 2 less than the parent material. And again, that's accounted for by this helium particle. So atomic mass is 2 less. Atomic number is 2 less as well, as we have that loss of that helium particle or the alpha particle. Beta decay, your number of protons is 1 more in the products. The atomic mass is the same. Um, you'll see the gamma symbol in the reaction. So we'll also have an alpha or beta particle. But the way that you'll know is you'll see that gamma symbol as well. So you guys have those pieces or those questions to work on in the workbook and then that worksheet. So that is your homework. Send it on to me when you're done. Okay, bye guys.